All right, thanks for having me out here, guys. Good morning to everybody. My name is Bruno Fong-Martinez, and I'll be presenting to you about corrosion inhibitors and lab and field samples. This was work recently done to finalize my PhD, so thankfully finished that in July. Best of luck to all fellow graduate students out here. There is a light at the end of the shotcrete tunnel, so hope you can get there soon. Even though I did finish my schooling recently, this is very much still research in progress. As I mentioned, we are testing field samples, which are often very long-term samples. These corrosion specimens, I think the most interesting data will come around the 8 to 10 year mark. Right now, they're about the 4-year mark. So right off the bat, we have a marine exposure block. That is what we like to make out here at the University of Texas. And this specimen, you can see, is suffering from very deep corrosion. This specimen itself has 4 embedded bars at 4 different depths: 1/2 inch, 1 inch, 1.5, and 2. And we can see already that obviously the cracking is a function of the depth. And this is what we're trying to avoid. The intent of this research was to use corrosion inhibitors in OPC mixes to improve their durability. This is part of a broader project intended to study the use of admixtures in improving durability in lieu of using SEMs, foreshadowing the less availability of fly ash in the future. So that's what we're going to be focusing on. Some quick background on corrosion. We focused on chloride-induced corrosion, which means that typically the chlorides will ingress externally from a sodium chloride solution, typically seawater or de-icing salts on roads. You have your concrete, reinforced concrete, which has a passive layer formed around the reinforcement. The sodium chloride ingresses with time, and it ingresses as a function of your diffusion coefficient, and it slowly progresses down the depth of your concrete until you reach a critical threshold, which is known as a chloride threshold. Once that chloride threshold is reached, basically your passivation is extinguished. You begin to form rust formations. These rust formations expand, crack the concrete, and once you have a cracked concrete, it's basically a free pass for to chloride splash mountain. So don't want to get to that extent. The use of corrosion inhibitors is meant to be a preventative application to delay corrosion. You can't really avoid it. It's going to happen, so the best you can do is to delay it. The damage model that we use is a bilinear in the sense that you have an initiation time at which the chlorides are ingressing. Then you hit your chloride threshold, the steel depassivates, and you have a period of propagation. So it's bilinear in the sense of nothing happens, and then boom, stuff starts happening. Propagation period sometimes can be estimated to be around 6 years, and during this time, you're going to have the buildup of that rust formation, and then can develop cracking, spalling, and eventual collapse. And that will be your service life of the structure. The intent of corrosion inhibitors is to extend this period by both delaying initiation of corrosion and reducing the slope of this line. So that's the main intent with corrosion inhibitors. As part of this project, we tested 3 products to use. We used a calcium nitrite inhibitor, which is your run-of-the-mill, over-the-counter corrosion inhibitor. It is meant to increase the chloride threshold, so it's not supposed to increase your diffusion coefficient or slow down the ingress. It's just supposed to have a higher threshold, a higher loading. We used a product P, what we will call product P, which is a calcium nitrate and calcium nitrite accelerator. It should be noted that this is labeled actually as an accelerator, so it is not labeled at all as a corrosion inhibitor, but some previous literature indicated that the calcium nitrate could act as calcium nitrite and serve as a corrosion inhibitor. The third product R, is an amines and esters inhibitor, which is intended to both reduce the permeability, so reduce your chloride diffusion, and increase your chloride threshold, so dual action on that one. We did a number of lab testing samples. So lab samples, again, are smaller samples that you have in a controlled lab environment. These are corrosion beams that go wetting and drying cycles. Right here, you see it is being ponded with a sodium chloride solution and dried. So there's cycles of wetting and drying. So the ingress of chlorides is not purely diffusion based. There's sorptivity and other factors associated. This sample on the right is a portion of a cylinder, a disc that was submerged in sodium chloride solution, and that one is purely diffusion based. We then profile layers off of the cylinder and get a profile for the chloride ingress as a function of depth. On the other hand, field samples are these big blocks, 300-pound blocks that we like to hang off of a seawall in the Gulf of Mexico down there in Texas. They're big samples, and then we put them out there. We do half cell measurements. We also profile them for chloride ingress, and there we see our friend the turtle providing forensic examination on our block. So these samples, again, are intended to represent the real world, what happens to a real structure undergoing real exposure to salt water. This is what the site looks like out there in Port Aransas, and it's a very unique site. It's very exciting that we have the opportunity to, just go out there to the beach and hang these blocks out there. Very much real world research. But what happens when you get into the real world? Well, sometimes things can get too real. We have lost a number of blocks for various reasons. In 2017, we had a hurricane hit the Gulf of Mexico, Hurricane Harvey, and we actually lost a number of blocks. Just the water, the waves just lifted the blocks off the chain, and off they go. You'll also notice that the chain out here is corroding. So we're intending and studying corrosion of reinforcement, but turns out our chains corrode too. So that led us to figure out different ways to hang the blocks. One of my ideas was to use rope, and unfortunately that also didn't fare too well. So we've had, again, a number of learning experiences with this site, but I think at this point we have a good idea of how to get the blocks out there and get them to stay. This is out here us. That's Professor Kevin Follier, my advisor, trying to rescue one of the blocks that fell. Thano and Rachel and myself. This is a contraption that we did so we could literally hand crank the blocks out of the water. Had to lift a number of blocks that way. Not too fun for my shoulder. So periodically we bring the blocks out of the water, bring them out on a trailer, bring them back to the lab, and then that's me profiling them layer by layer. 2-millimeter layers is the goal, the target, and then that way you create a plot of the depth of ingress of chlorides, and you create something that looks like this. So what I'm showing you is specifically the P product, which is the calcium nitrate, calcium nitrite. First you have your control, then you have your 2-gallon dosage, 4-gallon dosage, and 6-gallon dosage. I'll start with the control. We see that these are the test values, empirical test values, and then we apply a model to fit that data. We see that the control, at no point does the control is not able to mitigate the chlorides to the baseline point, which means that up to even 30 millimeters, we have a very high chloride content. A baseline chloride is basically the initial chloride of your concrete based on your constituents, your initial constituents, and as long as you don't use salt water or any chemicals with chlorides, you should be at a very low level, 0.01, 0.02. And obviously the control is not going to get there anytime soon. We see with the 2-gallon admixture that we're able to hit that baseline around 24 millimeters. You increase that dosage to 4, and you have no chlorides at 12 millimeters. At 6 gallons, you have that no chloride at about 7 or 8 millimeters. So this is fantastic results in the sense that we're seeing an improved effect with dosage. These are the diffusion coefficients for lab and field samples. Data is a bit messy, but the point I'm trying to show is that a low chloride diffusion is good in the sense that you're less permeable. And in this set of data, comparing lab and field samples, we see a tremendous connection between the lab and field data of the P admixture, the nitrate admixture. So again, we see tremendous effect of dosage, reducing your diffusion coefficient. In this case, in the P6 field sample, the diffusion coefficient is so low, it's not even visible at this scale. So the fact that we got this data to correlate in lab and field and for it to be consistent across dosages was very exciting. For the other samples, this is the nitrite admixture, which was not intended to reduce the diffusion coefficient, but we see that on average it did. It reduced it from the control, which is black, and then the third product, product R, is the blue one. We also did something I call chloride mapping that was performed on the corrosion beams, which basically meant that we saw cut the corrosion beams at a 1-inch depth. So again, the water was ponded up here, and at a 1-inch depth, you have your first layer of reinforcement, the top one. And then I drew a perimeter of the exposure area and called areas A, B, C, D, E. And we see that within the exposure perimeter, you have a tremendous loading of chlorides. Corrosion is estimated to start at a 0.07% chlorides. So obviously these numbers are off the charts. And we see that outside of the perimeter, I'll backtrack a little bit. These numbers are so high, it is assumed because of localized cracking. So once you have localized cracking, again, chlorides have a free pass and is not diffusion based. In the outside perimeter, we're assuming that this is diffusion based, and that's why we have more moderate chloride levels. So we did that for a few select beams, and we found some very interesting results with, again, the product P. So again, we have a control, and you have the product P at 6 gallons, which was very remarkably able to have no chlorides inside of your ponding zone. We also saw that it also had really high zones, and this was attributed more to, again, localized cracking. So the idea is that this admixture is doing a tremendous job at reducing chloride ingress when it's diffusion based, but obviously once you have cracking, then it's a game over. Up next, I have some forensic evaluation of the bars that we pulled out from that top reinforcement, and this is more to show just how difficult it can be to evaluate corrosion. Sometimes when you have extensive corrosion, visible corrosion on a bar, it's easy to see that you have a high chloride content and you have a very high voltage in terms of half-cell potential. So in this case, it's a 3 strikes. But sometimes you can have moderate corrosion visually, you can have low chloride contents locally, and a good value of half-cell potential. And sometimes it's a mixed bag of minor damage visually, medium voltage, and high chlorides. So in general, corrosion is very difficult to assess, and even using these 3 different methods, you can get conflicting evidence. This is the half-cell potential on the exposure block. So we're measuring voltage between a reference electrode at the top and the layer of bars, and we see we have the different depths at the bottom: 1/2 inch, 1 inch, 1.5, 2 inches. This is at 44 months exposure, about 3 years. And we see that we have low, uncertain, high probabilities of corrosion based on voltages. And we see that nothing at the 1/2 inch and the 1 inch will prevent corrosion in an OPC mix at those depths. However, the 1.5 and the 2 inches, that's where it's getting more interesting. And really, that's where we're going to need more time to assess what's going to happen 8 to 10 years down the line, which is more or less where I think the more important results are going to come out. And again, most structures are designed with a 2-inch cover, so the interesting results will come over here. But in the meantime, we see that our control is failing within 3 years. This is a summary of the testing that we did. I just presented very select few tests, but we did strength, resistivity, diffusion, half-cell, and service life models. In summary, I'll say that the product P, the nitrate product, did a tremendous job in lowering diffusion coefficients, and that greatly improved the service life model. The nitrite product, product D, is doing fairly well in terms of the half-cell potential. So we'll have to see if that maintains for the longer life of the specimens. And right here, I'll just address the issue that we are seeing a tremendous improvement in diffusion coefficient. However, this improvement is not reflected in resistivity or strength. So that is a bit of a conundrum we're trying to figure out. It's like, why, if you're getting a decreased permeability in terms of diffusion coefficient, why is that not being seen in resistivity and or strength? So in conclusion, we have the calcium nitrate, calcium nitrite product P, very interesting results because this product is not advertised as a corrosion inhibitor, it's advertised as an accelerator. However, we see that it significantly reduced chloride ingress, and that resulted in a very notable decrease in your diffusion coefficient, and that directly improved, and the improvement was directly related to the dosage and observed across lab and field samples, and this is like a unicorn for any researcher for your results to match dosage and be observed in multiple sample environments. We have some ideas about possible mechanisms of why this is happening. Potentially there's a permeability decrease and due to enhanced chloride binding or formation of hydration products with some pore blocking abilities. But again, resistivity and strength have not picked up on this, so we'll have to see what other testing can be done to get at this issue. In terms of the calcium nitrite, this is the regular corrosion inhibitor. We saw a reduced diffusion coefficient, which is not commonly attributed. Again, this product is mostly intended to increase your threshold. The threshold is a very difficult number to get at, but if it is the case that it is both a diffusion coefficient reduction and an increase in threshold, then there may be a synergistic effect between both of those factors. And again, we have the field samples, which will determine long-term performance and provide useful information in the long term. Again, 8 to 10 year range. References from the presentation, testing methods mentioned, and yeah, questions. Since this is the last presentation, it may be just easiest to email me if you have any questions. But yeah, thank you to everyone involved. I had a great time during my time at UT, and happy to continue that research for a while. And thank you, Professor O'Reilly and the rest of the ACI staff for putting this together.